Have you ever wondered if we are alone out here in the vastness of space? Not just as a species, but as a galaxy? What if I told you that our Milky Way is part of a family, a small gathering of galaxies gently bound together by invisible threads of gravity? Tonight, we take a peaceful journey through our immediate cosmic neighborhood, a place called the Local Group. Here, over 50 galaxies drift together in a slow, eternal dance, and each one has a story to tell. Come with me and let's meet our neighbors. Imagine for a moment that you could step outside our galaxy and look back at the cosmic landscape we call home. What would you see? You would not find the Milky Way floating alone in the darkness. Instead, you would discover something remarkable and comforting. We are part of a community. The local group is what astronomers call our galactic neighborhood, a collection of more than 80 galaxies all held together by the same fundamental force that keeps your feet on the ground: gravity. These galaxies span a region of space about 10 million light-years across, which sounds enormous until you realize how vast the universe truly is. In cosmic terms, we are huddled together in a small, intimate corner of creation. Why do galaxies form groups like this? The answer lies in the very beginning of time itself. After the Big Bang, matter was not distributed evenly across the expanding universe. There were regions slightly denser than others, and gravity began its patient work. Over billions of years, these dense regions pulled in more and more material, eventually forming the galaxies we see today. Some galaxies were born close enough to one another that their mutual gravitational attraction kept them bound together, creating what we now call galaxy groups and clusters. The local group is our particular cluster, and it has been our cosmic family for as long as the Milky Way has existed. We have been neighbors for 13 billion years. The local group is dominated by 3 large spiral galaxies. These are the giants of our neighborhood, the grand structures around which all the smaller galaxies orbit and dance. The Milky Way is one of these 3, and you might wonder where we rank in size and majesty. Are we the largest? Are we somewhere in the middle? The truth is both humbling and fascinating. While our galaxy is certainly impressive, containing hundreds of billions of stars and stretching over 100,000 light-years in diameter, we are not the biggest member of our family. That honor belongs to another galaxy, one that has captivated human imagination for centuries. But before we meet this grand neighbor, let us take a moment to appreciate our own home from the outside. Looking at the Milky Way from this perspective is a strange experience. Somewhere in one of those spiral arms, on a small rocky planet orbiting an average yellow star, you exist. Every human who has ever lived, every story ever told, every empire that has risen and fallen, all of it happened within this single island of stars. But the Milky Way is just one member of a larger community. As we pull back further, we begin to see the other galaxies of the local group appearing in the cosmic darkness. Some are large and bright, others are faint and small, barely visible ghosts drifting through space. Each one is unique, each one has its own character, and together they form a portrait of cosmic diversity and beauty. There is something deeply comforting about knowing we are not alone out here. The universe can feel overwhelmingly empty at times, a vast ocean of darkness punctuated by tiny islands of light. But within the local group, we have companions. We have neighbors who have existed alongside us for eons, sharing the same small patch of space-time. These galaxies have witnessed the same cosmic events we have. They have experienced the same expansion of the universe, the same flows of intergalactic gas, the same influences from nearby galaxy clusters. In a very real sense, we share a common history with every member of the local group. We are bound together not just by gravity, but by time itself. As we float here in the space between galaxies, taking in the view of our cosmic neighborhood, it is worth pausing to consider what a galaxy group truly represents. It is not just a random collection of objects that happen to be near each other. A galaxy group is a gravitationally bound system, meaning that all of its members are in motion relative to one another, orbiting around a common center of mass. This is the same principle that governs the planets orbiting the Sun, but on a scale millions of times larger. The galaxies of the local group are engaged in an ancient choreography, their movements dictated by the distribution of mass and the relentless pull of gravity. Some galaxies are moving toward us, others away, but all are part of the same cosmic dance. The local group is relatively small as galaxy groups go. Some groups contain hundreds of galaxies, packed closely together in regions of space not much larger than our own neighborhood. But perhaps there is a certain elegance to our group's modest size. We are large enough to be interesting, to contain a diverse array of galactic types and structures, yet small enough that we can still appreciate each member as an individual rather than just one face in a vast crowd. In the local group, every galaxy matters. Every galaxy has a role to play in the collective story. And as we continue our tour, we will meet each of these cosmic neighbors, from the grandest spirals to the tiniest dwarfs, and we will come to understand what makes each one special. Before we begin visiting individual galaxies, let us take one more moment to simply exist here in the quiet of intergalactic space. There is no sound here, no air, no reference points to judge your motion. You are suspended in the purest form of tranquility, surrounded by the soft glow of distant galaxies and the faint shimmer of starlight that has traveled for millions of years to reach this exact spot. This is the space between worlds, the void that connects rather than separates. And as we prepare to embark on our journey through the local group, remember that we are not traveling through emptiness. We are traveling through a neighborhood, a community, a family of galaxies that have shared the cosmos together since the beginning of time. Let us go meet them. Let us begin our tour at the most familiar place of all, our home, the Milky Way. From our vantage point here in intergalactic space, we can see it in its entirety, something that would be impossible from within. The Milky Way is a barred spiral galaxy, a grand cosmic pinwheel rotating slowly through space. Its spiral arms are rich with glowing nebulae, nurseries where new stars are being born even as we speak. The central bar, a dense rectangular structure of older stars, cuts through the galactic core, and from this bar, the spiral arms gracefully unfurl. The whole structure is about 100,000 light-years in diameter and contains somewhere between 200 billion and 400 billion stars. Among those billions of stars, one particular yellow dwarf harbors a planet where you and I have our existence. The Milky Way is not a static structure frozen in time. It is alive with motion and change. The galaxy rotates, but not like a solid disk. Different parts of the galaxy orbit the galactic center at different speeds, creating a differential rotation that maintains the spiral pattern. Stars are born, live their lives, and die, recycling their material back into the interstellar medium to form new generations of stars. Gas clouds collapse under their own gravity, supernova explosions scatter enriched material across space, and black holes lurk at the hearts of dense star clusters. This is a dynamic, evolving system, and it has been changing and growing for over 13 billion years since its formation in the early universe. We are witnessing just one moment in the long life of our galaxy. At the very center of the Milky Way lies something extraordinary, a supermassive black hole. This object, known as Sagittarius, AC, contains the mass of over 4 million suns compressed into a region smaller than the orbit of Mercury. It is invisible, detectable only by its gravitational influence on the stars that orbit it at tremendous speeds. This central black hole is not unique to our galaxy. Nearly every large galaxy in the universe harbors a supermassive black hole at its core, and these enigmatic objects play a crucial role in galactic evolution. They regulate star formation, they eject enormous amounts of energy during periods of active feeding, and they serve as gravitational anchors around which the rest of the galaxy organizes itself. The Milky Way's central black hole is currently quiet, dormant, but it has not always been so. The Milky Way is surrounded by a halo, a vast spherical region extending far beyond the visible disk. This halo contains globular clusters, ancient collections of stars that formed in the very early universe, as well as streams of stars torn from smaller galaxies that the Milky Way has consumed over billions of years. Our galaxy is a cannibal, having grown to its current size by merging with and absorbing smaller galaxies throughout cosmic history. The evidence of these ancient mergers is written in the halo, where stellar streams trace out the orbits of long-destroyed dwarf galaxies. This process of galactic cannibalism is common in the universe, and it is one of the primary ways that large galaxies like ours grow over time. We are, in a very real sense, an amalgamation of many smaller galaxies. The disk of the Milky Way is divided into several distinct regions, each with its own character. The thin disk where we reside is rich in gas and dust and is the site of active star formation. The thick disk, composed of older stars, lies above and below the thin disk and represents an earlier era in the galaxy's history. The bulge, that bright central region we can see from here, is densely packed with ancient red and yellow stars, some of the oldest in the entire galaxy. And then there is the dark matter halo, invisible and mysterious, containing far more mass than all the visible stars combined. This dark matter provides the gravitational scaffolding that holds the entire galaxy together, yet we still do not fully understand what it is made of. It is one of the great mysteries of modern astronomy. Within the local group, the Milky Way is the second largest galaxy. We are massive and luminous, containing more stars than most of our neighbors, but we are not the undisputed giant of our neighborhood. That distinction belongs to another galaxy, one that we will visit soon. Still, our galaxy is nothing to be modest about. The Milky Way is a mature, well-developed spiral galaxy in the prime of its existence. We are still forming new stars at a healthy rate. Our structure is stable and well-organized, and we possess a rich diversity of stellar populations spanning the entire history of the universe. In many ways, the Milky Way represents the typical large spiral galaxy, and by studying our home in detail, astronomers can learn about spiral galaxies throughout the cosmos. There is something profound about seeing your home from the outside. When we look at the Milky Way from this perspective, it is easy to feel a sense of detachment, as if we are observing something separate from ourselves. But the opposite is true. We are deeply embedded in this galaxy. Every atom in your body was forged in the heart of a star that once existed somewhere in this spiral structure. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars that lived and died within the Milky Way. You are not separate from the galaxy. You are made of the galaxy. You are a way for the Milky Way to know itself, to observe itself, to marvel at its own existence. This is not poetry. This is the literal scientific truth of what you are. As we prepare to leave our home galaxy and continue our tour of the local group, take one last look at the Milky Way. Where you come from. This is the structure that has nurtured life, enabled consciousness, and allowed for the possibility of this very moment where you can contemplate your own cosmic origins. The Milky Way is not just our address in the universe. It is our parent, our cradle, our foundation. And no matter how far we travel through the cosmos, no matter what wonders we encounter, this will always be the place we call home. Now, let us turn our attention outward and meet our neighbors, beginning with the largest and most magnificent member of our local family. Let us journey to Andromeda. As we drift through the intergalactic void, leaving the Milky Way behind us, another magnificent structure begins to dominate our view. It grows larger and brighter as we approach, revealing itself to be even more massive than our own galaxy. This is Andromeda, also known by its catalogue designation M31, and it is the largest galaxy in the local group. Andromeda is a true giant, containing over 1 trillion stars, more than twice the stellar population of the Milky Way. It stretches approximately 220,000 light-years in diameter, making it substantially larger than our home galaxy. For billions of years, Andromeda and the Milky Way have been the twin pillars of the local group, the two dominant structures around which all the smaller galaxies orbit. But Andromeda holds the crown as the supreme member of our cosmic family. Andromeda is visible from Earth with the naked eye on clear, dark nights, appearing as a faint smudge in the constellation that shares its name. Ancient astronomers recorded its presence, though they had no idea what they were looking at. It was not until the early 20th century that we realized Andromeda was not a nebula within our own galaxy, but an entirely separate island universe, a galaxy in its own right, lying far beyond the boundaries of the Milky Way. This discovery fundamentally changed our understanding of the cosmos. The universe was suddenly much larger than anyone had imagined. Andromeda was the first galaxy we recognized as being separate from our own, and it remains the most studied external galaxy in all of astronomy. It has taught us nearly everything we know about how large spiral galaxies function and evolve. Like the Milky Way, Andromeda is a barred spiral galaxy, though its structure is slightly different from our own. The spiral arms are tightly wound, creating a more orderly appearance, and the galactic disk shows evidence of complex interactions with smaller satellite galaxies over billions of years. Andromeda's disk is warped and distorted in places, a sign that it has experienced mergers and close encounters throughout its history. In fact, Andromeda appears to have had a more violent past than the Milky Way, having consumed several large galaxies over the past few billion years. These mergers have contributed to its enormous size and mass, and they have also triggered bursts of star formation that are visible in certain regions of the galaxy. Andromeda is a survivor, a conqueror, a galaxy that has grown powerful through cosmic conquest. At the heart of Andromeda lies not one, but two supermassive black holes. This double black hole system is the result of a past merger with another large galaxy, and eventually, over the course of millions of years, these two black holes will spiral together and merge into a single, even more massive black hole. The process will release tremendous amounts of gravitational wave energy, ripples in the fabric of space-time itself that will propagate across the universe. This future merger of black holes is just one of many dramatic events waiting in Andromeda's future. But that is a story for later. For now, we can simply appreciate the strangeness of a galaxy with two hearts, two central engines of gravity and power. It is a unique configuration, a temporary state in the long evolution of a galaxy. Andromeda is surrounded by its own retinue of satellite galaxies, smaller companions that orbit the giant-like moons around a planet. The two most prominent satellites are M32 and M11, both dwarf elliptical galaxies that are easily visible in amateur telescopes from Earth. M32 is particularly interesting because it appears to be the remnant core of a once much larger galaxy that was torn apart by Andromeda's gravity during a close encounter. What we see today is just the dense central region, the indestructible heart of a galaxy that otherwise no longer exists. These satellite galaxies add to the complexity and beauty of the Andromeda system, creating a miniature version of the local group structure around the dominant central galaxy. Andromeda, like the Milky Way, is not alone. It has its own family. The distance between the Milky Way and Andromeda is approximately 2.5 million light-years. This means that the light we see from Andromeda today left the galaxy 2.5 million years ago, during a time when our human ancestors were just beginning to walk upright on the plains of Africa. We are looking at Andromeda's past, seeing it as it was long before modern humans existed. And yet, in cosmic terms, 2.5 million light-years is not very far at all. Andromeda is our nearest large galactic neighbor, close enough that we can study it in exquisite detail, close enough that we can resolve individual stars within its structure. This proximity makes Andromeda invaluable to astronomers. It is a laboratory where we can test our theories about galaxy formation and evolution, seeing processes play out that are too difficult to observe in more distant galaxies. One of the most remarkable things about Andromeda is that it is moving toward us. Unlike most galaxies in the universe, which are receding from us due to the expansion of space, Andromeda is approaching. Its blue-shifted spectrum tells us that it is traveling through space in our direction at about 110 kilometers per second. This might sound fast, and it is, but on the scale of intergalactic distances, it is a leisurely pace. Still, Andromeda's approach means that our two galaxies are on a collision course. In approximately 4 to 5 billion years, the Milky Way and Andromeda will merge together, creating a single, massive elliptical galaxy. This is not a catastrophe. It is simply the next chapter in the story of our local group, but we will discuss this cosmic collision in more detail later in our journey. For now, simply know that Andromeda is coming to visit. Standing here in the space between our two galaxies, we can appreciate the majesty of Andromeda in a way that is impossible from within the Milky Way. From Earth, it appears as a small, faint patch of light, but from here, we can see it for what it truly is. A colossal structure of 1 trillion suns, a self-contained universe of stars and worlds and possibilities. We can see the delicate spiral arms traced out in blue starlight, the warm glow of the central bulge, the dark dust lanes that paint shadows through the galactic disk. We can see the globular clusters that orbit the galaxy like a swarm of fireflies, and the satellite galaxies that dance in attendance around their giant host. Andromeda is magnificent, and it is our neighbor. Let us continue our tour and meet the other members of our cosmic family. Our next destination lies a bit further out in the local group, but it is no less worthy of our attention. The Triangulum galaxy, known as M33, is the third largest member of our local family. While it cannot compete with the Milky Way or Andromeda in terms of sheer size and mass, Triangulum possesses a beauty and grace all its own. It is a spiral galaxy, but unlike the tightly wound spirals of Andromeda, Triangulum's arms are loose and open, giving it a more delicate, almost ethereal appearance. The galaxy contains somewhere between 40 and 50 billion stars, making it substantially smaller than its two larger cousins, but still a respectable galaxy by any measure. Triangulum is sometimes overlooked in discussions of the local group, overshadowed by the magnificence of Andromeda and the familiarity of the Milky Way, but this is a galaxy that deserves recognition. Triangulum is actively forming new stars at a rate higher than either the Milky Way or Andromeda. The galaxy is rich in gas and dust, the raw materials needed for star formation, and throughout its spiral arms we can see the bright glow of massive young stars and the pink nebulae where new stars are currently being born. One region in particular, known as NGC 604, is one of the largest and brightest star-forming regions in the entire local group. This single nebula is larger than the Orion Nebula, larger than the Tarantula Nebula in the large Magellanic Cloud, a true stellar factory producing hundreds of massive stars. NGC 604 is so bright that if Triangulum were at the same distance as the Orion Nebula, this single star-forming region would be visible to the naked eye and would rival the brightest stars in our night sky. It is a reminder that even the smaller members of the local group can host extraordinary phenomena. Triangulum has an interesting relationship with Andromeda. The two galaxies are relatively close to each other, and there is evidence that they have interacted gravitationally in the past. Some astronomers believe that Triangulum may actually be a satellite galaxy of Andromeda, gravitationally bound to the larger galaxy and orbiting it over the course of billions of years. Others suggest that Triangulum is an independent member of the local group, following its own path through space. The truth is that we are still not entirely certain of Triangulum's orbital status. The motions of galaxies are complex, and determining precise three-dimensional velocities across millions of light-years is extremely challenging. What we do know is that Triangulum, Andromeda, and the Milky Way are all moving relative to one another in a complex gravitational dance, and their futures are intimately connected. One of the most interesting features of Triangulum is that it appears to lack a supermassive black hole at its center. Most large galaxies have such a black hole, but if Triangulum has one, it is much smaller and less massive than expected for a galaxy of its size. This is puzzling and suggests that Triangulum may have formed and evolved in a slightly different way than typical spiral galaxies. Perhaps it has never experienced the major mergers that seem to be necessary for building very massive central black holes. Or perhaps the black hole is there but is simply dormant and difficult to detect. Whatever the explanation, Triangulum stands as an example of the diversity of galaxy types and evolutionary paths. Not all galaxies follow the same script. Each one is an individual, shaped by its unique history and circumstances. Triangulum is visible from Earth with binoculars or a small telescope, and under exceptionally dark skies it can be glimpsed with the naked eye. It holds the distinction of being the most distant object that can be seen without optical aid, lying approximately 3 million light-years from Earth. When you see that faint smudge of light in the constellation Triangulum, you are seeing light that left the galaxy 3 million years ago, during the Pliocene epoch on Earth, when our early ancestors were still evolving in Africa. That light has traveled across the vast emptiness of intergalactic space, surviving for millions of years without being absorbed or scattered, just to enter your eye at this particular moment. It is a connection across time and space, a photon's journey from one corner of the local group to another, and you are the endpoint of that cosmic voyage. When we look at the structure of Triangulum from our vantage point here in space, we can see that it is oriented nearly face-on to us, meaning we are seeing it from above rather than edge-on. This favorable viewing angle has made Triangulum one of the best-studied spiral galaxies in the sky. Astronomers can trace individual star-forming regions, measure rotation curves to determine the distribution of mass, and study the chemical composition of the interstellar medium. Triangulum has become a benchmark galaxy, a standard against which we compare models of galaxy formation and evolution. It may be the third largest member of the local group, but in terms of scientific importance, it ranks alongside Andromeda and the Milky Way as one of the most valuable galaxies in the local universe. Sometimes, the quiet members of a family have the most to teach us. The fate of Triangulum in the distant future is uncertain. When the Milky Way and Andromeda collide billions of years from now, what will happen to this third spiral galaxy? Will it be swept up in the merger, adding its stars to the mix and becoming part of the new combined galaxy? Or will it be flung outward by gravitational interactions, escaping the collision and continuing on as an independent galaxy? Computer simulations suggest different outcomes depending on the precise initial conditions, and we simply do not know enough about the three-dimensional motions and masses of all the galaxies involved to make a definitive prediction. Triangulum's future is an open question, a reminder that even in the orderly realm of celestial mechanics, there is still room for uncertainty and surprise. The universe does not always follow predictable paths. As we prepare to leave Triangulum and continue our exploration of the local group, take a moment to appreciate this often overlooked galaxy. It may not have the size of Andromeda or the personal connection we feel to the Milky Way, but Triangulum has its own unique character and beauty. Its loose spiral arms, its vigorous star formation, its uncertain relationship with its larger neighbors, all of these things make Triangulum special. In a family of galaxies, every member contributes something to the whole, and Triangulum's contribution is a reminder that there are many ways to exist as a galaxy, many paths through cosmic time, and many stories yet to be told. Now, let us turn our attention to some of the smaller members of our local family, the dwarf galaxies that orbit around the giants like children around their parents. Let us visit the Magellanic Clouds. We now journey to a very different type of galaxy. The Large Magellanic Cloud, often abbreviated as the LMC, is one of the most prominent satellite galaxies of the Milky Way. It is visible from the southern hemisphere as a faint, hazy patch in the night sky, and for millennia, observers in the southern latitudes have known of its existence. The galaxy is named after the explorer Ferdinand Magellan, whose expedition around the globe brought European attention to this southern sky treasure. The LMC is not a spiral galaxy like the three we have visited so far. It is classified as an irregular dwarf galaxy, lacking the organized structure and symmetry of spirals and ellipticals. Instead, it is a chaotic, asymmetric collection of stars, gas, and dust, shaped by its interactions with the Milky Way and its smaller companion, the Small Magellanic Cloud. The Large Magellanic Cloud lies only about 160,000 light-years from the Milky Way, making it one of our closest galactic neighbors. At this distance, the LMC is close enough that we can resolve individual stars within it using modern telescopes, and this proximity has made it an invaluable laboratory for studying stellar evolution and astrophysics. The LMC contains a rich diversity of stellar populations, from ancient globular clusters to young, massive stars still embedded in their birth nebulae. It is a miniature version of a full galaxy, compressed into a space about 14,000 light-years across, and it offers astronomers the opportunity to study galactic processes in detail that would be impossible to achieve in more distant systems. The Large Magellanic Cloud is small, but it is scientifically mighty. One of the most famous features of the Large Magellanic Cloud is the Tarantula Nebula, also known as 30 Doradus. This is one of the most active star-forming regions in the entire local group, a massive complex of gas and dust where thousands of stars are currently being born. At the heart of the Tarantula Nebula lies a dense cluster of extremely massive stars, some of the most massive stars known to exist anywhere in the universe. These stellar behemoths are burning through their fuel at prodigious rates, and they will live only a few million years before exploding as supernovae. The Tarantula Nebula glows with the combined light of all these young stars, and if it were located at the distance of the Orion Nebula, it would cast shadows on Earth and be visible during the daytime. It is a monument to the power and fury of star formation. The Large Magellanic Cloud played a crucial role in one of the most important astronomical events of the modern era. In 1987, a star in the LMC exploded as a supernova, an event designated SN 1987A. This was the nearest supernova to Earth since the invention of the telescope, and it was visible to the naked eye for several months. Astronomers around the world turned their instruments toward the LMC to study the explosion, and SN 1987A became the most intensely observed supernova in history. The data gathered from this event revolutionized our understanding of how massive stars die and how supernovae produce the heavy elements that are essential for life. 1987A also confirmed the existence of neutrinos, ghostly subatomic particles that escape from the collapsing core of a dying star. The remnant of SN 1987A is still visible today, a glowing ring of material expanding into space. The Large Magellanic Cloud is not an isolated system. It is gravitationally bound to both the Milky Way and the Small Magellanic Cloud, forming a trio of galaxies engaged in a complex gravitational interaction. As the LMC orbits the Milky Way, tidal forces from our galaxy's gravity are pulling streams of gas out of the LMC, creating what astronomers call the Magellanic Stream. This is a vast trail of neutral hydrogen gas stretching across the southern sky, marking the orbital path of the LMC over hundreds of millions of years. The Magellanic Stream is evidence that the LMC is slowly being torn apart by its larger companion, and eventually, over the course of billions of years, the large Magellanic Cloud will likely be consumed entirely by the Milky Way. It will become just another stellar stream in our galaxy's halo, a memory of a once independent dwarf galaxy. Despite being classified as a dwarf irregular galaxy, the large Magellanic Cloud shows hints of structure that suggest it may have once been a barred spiral galaxy. There is a bar-like feature running through the central region, and some astronomers believe that interactions with the Milky Way and the small Magellanic Cloud have disrupted what was once a more organized spiral structure. If this is true, then the LMC is an example of how galactic interactions can fundamentally change a galaxy's morphology, transforming it from one type to another. The universe is not static. Galaxies evolve, they interact, they merge and transform. The large Magellanic Cloud is a work in progress, caught in the middle of a long transformation that will ultimately see it absorbed into the Milky Way. We are witnessing just one chapter in a story that spans billions of years. The large Magellanic Cloud is home to a rich population of globular clusters, ancient collections of stars that formed in the early universe. Some of these clusters are nearly as old as the universe itself, containing stars that have been shining for over 12 billion years. By studying these globular clusters, astronomers can learn about the early chemical evolution of the LMC and how dwarf galaxies like it formed and grew in the first few billion years after the Big Bang. The globular clusters in the LMC are not as massive or as densely packed as those in the Milky Way, but they provide a valuable comparison that helps astronomers understand the diversity of globular cluster populations throughout the local group. Every galaxy, no matter how small, carries within it the memory of the early universe, death. As we drift away from the large Magellanic Cloud, we can appreciate it for what it truly is. A small, irregular galaxy locked in a slow dance with a much larger partner, gradually being pulled apart and consumed. It is a poignant reminder of the cycle of galactic life and death that plays out across the universe. Galaxies merge and grow, absorbing smaller companions to build their mass. The large Magellanic Cloud has been a loyal satellite to the Milky Way for billions of years, and in billions more it will become part of our galaxy, its stars joining the vast population of the Milky Way's halo. This is not a tragedy. It is simply the way galaxies evolve. And as we continue our tour, we will meet the LMC's smaller companion, a galaxy that shares the same fate and the same slow, inexorable journey into the Milky Way. Let us visit the small Magellanic Cloud. A short distance from the large Magellanic Cloud, we find its smaller sibling. The Small Magellanic Cloud, or SMC, is another irregular dwarf galaxy orbiting the Milky Way. It is smaller and less massive than the LMC, containing only a few billion stars compared to the LMC's 30 billion or so. The SMC lies approximately 200,000 light-years from the Milky Way, making it slightly more distant than its larger companion. From Earth's southern hemisphere, the SMC appears as a fainter patch of light near the LMC, and together, the two Magellanic Clouds have been familiar features of the southern night sky for as long as humans have gazed upward. Like the LMC, the Small Magellanic Cloud is an irregular galaxy, lacking the symmetry and structure of spirals or ellipticals. Its shape has been distorted by tidal interactions with both the large Magellanic Cloud and the Milky Way. The Small Magellanic Cloud has a particularly distorted structure, stretched and elongated by the gravitational influence of its larger companion. In fact, observations suggest that the SMC may not be a single object at all, but rather two or more distinct concentrations of stars at different distances, aligned along our line of sight to create the appearance of a single elongated structure. This complex geometry is a result of the violent interactions between the SMC, the LMC, and the Milky Way. These three galaxies are engaged in a gravitational tug-of-war, and the SMC, being the smallest and least massive of the trio, has suffered the most dramatic distortions. Its stars are spread out over a larger volume of space than would be expected for a single coherent galaxy, and its future is uncertain. One of the most interesting characteristics of the Small Magellanic Cloud is its chemical composition. The SMC has a lower abundance of heavy elements compared to the Milky Way, the LMC, or most other galaxies in the local group. In astronomical terms, we say it has a lower metallicity. This means that the SMC contains proportionally more hydrogen and helium, the primordial elements created in the Big Bang, and proportionally fewer of the heavier elements like carbon, oxygen, and iron that are created inside stars. The low metallicity of the SMC tells us that it has not undergone as many generations of star formation and chemical enrichment as larger galaxies. It is, in a sense, more primitive, closer in composition to the early universe. This makes the SMC a valuable laboratory for studying how star formation proceeds in chemical environments similar to those that existed billions of years ago. Despite its small size and low mass, the Small Magellanic Cloud is actively forming new stars. Throughout its structure, we can see bright blue clusters of young, massive stars, as well as pink nebulae where star formation is currently underway. The star formation rate in the SMC is lower than in the LMC, but it is still significant, and it provides astronomers with examples of how stars form in low metallicity environments. This is particularly important for understanding the first generations of stars that formed in the early universe, which also existed in low metallicity conditions. By studying the SMC, we can gain insights into processes that occurred when the universe was young. The Small Magellanic Cloud is a window into the past, a place where we can see conditions that resemble those of the early cosmos. The Small Magellanic Cloud, like its larger companion, is contributing to the Magellanic Stream. As the SMC orbits the Milky Way, tidal forces strip away gas from the galaxy, adding to the long trail of neutral hydrogen that stretches across the southern sky. The SMC is being slowly dismembered by the gravitational forces acting upon it, and over billions of years, it will likely be completely torn apart. Some of its stars will be absorbed by the large Magellanic Cloud, while others will be scattered throughout the halo of the Milky Way. The gas stripped from the SMC will eventually rain down onto the Milky Way's disk, where it will fuel future generations of star formation. In this way, the Small Magellanic Cloud will not truly disappear. Its material will be recycled, becoming part of new stars and planets in the Milky Way. The Small Magellanic Cloud contains several notable astronomical objects that have contributed to our understanding of the universe. One of the most famous is a star known as a Cepheid variable, a type of pulsating star whose brightness varies in a regular, predictable manner. In the early 20th century, astronomer Henrietta Swan Leavitt studied Cepheid variables in the SMC and discovered a relationship between their pulsation period and their intrinsic luminosity. This discovery provided astronomers with a powerful tool for measuring distances across the universe, and it was this very technique that allowed Edwin Hubble to determine that Andromeda was a separate galaxy far beyond the Milky Way. The Small Magellanic Cloud, through the Cepheid variables it harbors, played a crucial role in expanding our understanding of the scale and structure of the universe. From a small, irregular dwarf galaxy came a discovery that changed everything. The relationship between the Small Magellanic Cloud and the Large Magellanic Cloud is complex. For a long time, astronomers believed that the two galaxies were gravitationally bound to each other, forming a binary pair that orbited the Milky Way together. Recent observations and simulations suggest a more complicated picture. The two clouds may have had close encounters in the past, but they may not be permanently bound to each other. Instead, they might be on separate, independent orbits around the Milky Way, and their current proximity is simply a temporary alignment. The gravitational interactions between the SMC, LMC, and the Milky Way are challenging to model precisely, and there is still much we do not understand about the orbital dynamics of these systems. What is clear is that all three galaxies are influencing each other, shaping each other's structures and futures in profound ways. As we leave the Small Magellanic Cloud and continue our journey through the local group, we can reflect on what we have learned from this small, humble galaxy. The SMC may be one of the least massive members of our cosmic family, but it has contributed enormously to our understanding of the universe. From Cepheid variables to low metallicity star formation, from tidal streams to the complex dynamics of satellite galaxies, the small Magellanic Cloud has been a teacher and a guide. It reminds us that size is not the only measure of importance. Even the smallest galaxies have stories to tell and lessons to impart. Now, let us turn our attention to the even smaller members of the local group, the dwarf galaxies that populate the outskirts of our neighborhood. Let us explore the realm of the dwarfs. We now enter a different realm of the local group, the domain of the dwarf galaxies. These are small, faint systems containing anywhere from a few million to a few billion stars, and they vastly outnumber the large galaxies in our neighborhood. In fact, the majority of galaxies in the local group are dwarfs, and this is true throughout the universe. Dwarf galaxies are the most common type of galaxy, yet they are often overlooked because they are so faint and difficult to observe. The local group contains over 80 known members, and most of them are dwarfs. These small galaxies come in two main varieties: dwarf elliptical galaxies and dwarf irregular galaxies. Let us begin by exploring the dwarf ellipticals, ancient relics that hold clues to the early history of galaxy formation. Dwarf elliptical galaxies are smooth, featureless systems composed primarily of old stars. They contain very little gas or dust, and they have not formed new stars for billions of years. In appearance, they resemble miniature versions of giant elliptical galaxies, but their formation history and evolutionary path are quite different. Dwarf ellipticals are common satellites of large galaxies, orbiting around giants like the Milky Way and Andromeda. The Milky Way has several dwarf elliptical companions, and Andromeda has even more. These small galaxies are often found in the outer halos of their host galaxies, moving on long elliptical orbits that take them far out into intergalactic space before swinging back in close to their massive companions. They are quiet, peaceful systems, having long ago exhausted their supplies of gas and ceased their star-forming activity. One of the most studied dwarf elliptical galaxies in the local group is Fornax. This small galaxy orbits the Milky Way at a distance of about 460,000 light-years, making it one of the more distant satellites of our galaxy. Fornax is home to 6 globular clusters, ancient spherical collections of stars that are among the oldest objects in the entire local group. These globular clusters are remarkable because they appear to be older than the galaxy itself, a puzzling situation that suggests Fornax may have formed through the merger of even smaller protogalactic fragments in the early universe. The presence of these globular clusters makes Fornax particularly valuable for studying the formation and early evolution of dwarf galaxies. It is a fossil, preserving information about processes that occurred over 12 billion years ago. Another notable dwarf elliptical in our neighborhood is Sculptor, one of the first dwarf galaxies to be discovered. Sculptor is closer to the Milky Way than Fornax, lying at a distance of about 290,000 light-years. It is a very faint galaxy, containing only about a few million stars, and it is composed almost entirely of old, metal-poor stellar populations. Sculptor has been extensively studied by astronomers interested in understanding the nature of dark matter because, like all dwarf galaxies, it appears to contain far more mass than can be accounted for by its visible stars. The stars in Sculptor are moving faster than they should be based on the gravitational pull of the visible matter alone, indicating the presence of large amounts of dark matter. Dwarf elliptical galaxies like Sculptor are among the most dark matter-dominated systems in the universe. How did dwarf elliptical galaxies form? This is one of the key questions in extragalactic astronomy. There are two main theories. The first suggests that dwarf ellipticals formed as small, independent galaxies in the early universe and have simply evolved in isolation, never accreting enough material to grow into larger systems. The second theory proposes that many dwarf ellipticals are the remnants of larger galaxies that have been stripped of their gas and outer stars through interactions with massive companions. In this scenario, a dwarf irregular or dwarf spiral galaxy falls into orbit around a giant galaxy, and tidal forces and ram pressure from the intergalactic medium remove the gas and disrupt the stellar disk, leaving behind a smooth, gas-poor remnant that we classify as a dwarf elliptical. The truth may be that both processes occur, and different dwarf ellipticals have different origins. The dwarf elliptical galaxies orbiting Andromeda are similar to those around the Milky Way. M32 and NGC 2005, the two most prominent satellites of Andromeda, are both dwarf ellipticals, although M32 in particular may have a more complex history. As we mentioned earlier, M32 appears to be the dense core of a once much larger galaxy that was disrupted by a close encounter with Andromeda. Its compact size and high central density make it unusual among dwarf ellipticals, and it serves as a reminder that the evolutionary paths of these small galaxies can be quite varied. Some dwarf ellipticals have lived quiet, uneventful lives in the outskirts of galaxy groups. Others have experienced violent interactions and transformations. Each galaxy has its own unique history written in the properties of its stars. Dwarf elliptical galaxies are important for testing our models of galaxy formation and cosmology. According to the standard model of cosmology, large galaxies like the Milky Way should have hundreds of small dark matter halos orbiting them, and each of these halos should potentially host a dwarf galaxy. However, we observe far fewer dwarf galaxies than this model predicts. This is known as the missing satellites problem, and it is one of the outstanding puzzles in cosmology. There are several proposed solutions. Perhaps many of the predicted small dark matter halos never formed stars and remained dark. Perhaps star formation in the smallest halos was suppressed by the reionization of the universe. Or perhaps our understanding of dark matter is incomplete. By studying the dwarf elliptical galaxies we can observe, astronomers hope to solve this puzzle and refine our understanding of how galaxies form. As we drift past these ancient, quiet dwarf elliptical galaxies, we can sense the deep time they represent. These are some of the oldest stellar systems in the universe, containing stars that formed when the cosmos was less than 1 billion years old. The light from these galaxies has been shining steadily for over 12 billion years, a testament to the longevity of low-mass stars. Dwarf ellipticals may be small and faint, but they are survivors. They have endured for nearly the entire history of the universe, witnessing the rise and fall of countless generations of stars, the formation and evolution of larger galaxies, and the gradual expansion of space itself. They are living fossils, and by studying them, we touch the very earliest epochs of cosmic history. Now, let us turn to the other type of dwarf galaxy, the irregular dwarfs, which present a very different picture. Unlike their elliptical cousins, dwarf irregular galaxies are young, active, and chaotic. These are small galaxies that still contain significant amounts of gas and dust, and they are actively forming new stars. The Magellanic Clouds, which we visited earlier, are examples of dwarf irregular galaxies, though they are among the largest and most massive of this class. The typical dwarf irregular is much smaller and fainter, containing anywhere from a few million to a few 100 million stars. What distinguishes dwarf irregulars from dwarf ellipticals is their ongoing star formation and their irregular asymmetric shapes. These galaxies lack the smooth, organized structure of ellipticals or the grand spiral patterns of large galaxies. Instead, they are messy, patchy collections of stars, gas, and nebulae shaped by internal processes and external interactions. One of the nearest dwarf irregular galaxies to the Milky Way is Leo T. This tiny galaxy was discovered only in 2006, despite its proximity, because it is so faint and diffuse. Leo T lies about 1.4 million light-years from the Milky Way and contains only a few 100,000 stars. It is remarkable for still having significant amounts of neutral hydrogen gas, despite its small size and low mass. This gas fuels ongoing star formation, and Leo T has small pockets where new stars are currently being born. The existence of galaxies like Leo T raises interesting questions about how such small systems manage to retain their gas in the face of various processes that would normally strip it away, such as ram pressure from the intergalactic medium or supernova-driven winds from star formation. Leo T is a survivor, clinging to its gas and continuing to create new stars against the odds. Dwarf irregular galaxies are chemically less evolved than larger galaxies. They have lower metallicities, meaning they contain proportionally less of the heavy elements created by previous generations of stars. This makes them valuable laboratories for studying the process of chemical enrichment in galaxies. As stars form, live, and die, they produce heavy elements through nuclear fusion in their cores and through supernova explosions. These elements are then mixed back into the interstellar medium, enriching the gas from which the next generation of stars will form. In dwarf irregular galaxies, this process is less advanced and the chemical composition more closely resembles that of the early universe. By studying star formation in these low metallicity environments, astronomers can gain insights into how the first galaxies formed and evolved billions of years ago. The star formation rates in dwarf irregular galaxies are low in absolute terms, but when normalized to the total mass of the galaxy, they can be quite high. These small galaxies are efficient at converting their gas into stars, even if the total number of stars they produce is modest. This efficiency is somewhat surprising given that dwarf irregulars have shallow gravitational potential wells, making it easier for gas to be ejected from the galaxy by supernova explosions and stellar winds. The fact that they retain enough gas to continue forming stars suggests that they must be accreting fresh gas from the intergalactic medium, or that their star formation proceeds in bursts with long quiescent periods in between. Understanding the star formation history of dwarf irregular galaxies is an active area of research with implications for our understanding of galaxy evolution in general. Many dwarf irregular galaxies show evidence of triggered star formation, where the collapse of gas clouds into stars is initiated by external influences such as gravitational interactions with other galaxies or the compression of gas due to motion through the intergalactic medium. These triggered bursts of star formation can create chains or arcs of young star clusters, visible as bright blue regions against the fainter background of older stars. The local group contains several examples of dwarf irregulars that appear to be undergoing such interactions, their structures distorted and their star formation enhanced by the gravitational influence of larger neighbors. These interactions are a key driver of evolution in small galaxies, shaping their star formation histories and ultimately determining whether they will survive as independent systems or be consumed by larger galaxies. Like dwarf ellipticals, dwarf irregular galaxies are also dark matter-dominated systems. The stars and gas we can see represent only a small fraction of the total mass of these galaxies. Most of their mass is in the form of dark matter, an invisible substance that interacts with normal matter only through gravity. The presence of dark matter in dwarf irregular galaxies is inferred from the motion of their stars and gas, which move faster than would be expected based on the gravitational pull of the visible matter alone. Understanding the distribution and properties of dark matter in these small galaxies is crucial for testing theories of dark matter and galaxy formation. Some theories predict that dwarf galaxies should have dense central concentrations of dark matter, while others predict more diffuse distributions. Observations of dwarf irregulars in the local group are helping to distinguish between these competing models. The future of dwarf irregular galaxies in the local group is varied. Some will continue to orbit their larger companions, gradually losing their gas through tidal stripping and ram pressure, eventually transforming into dwarf ellipticals once their star formation ceases. Others may experience close encounters with larger galaxies that will disrupt their structures entirely, scattering their stars and adding them to the stellar halos of the Milky Way or Andromeda. A few may even escape the local group entirely, flung outward by gravitational interactions to wander the intergalactic void as isolated systems. The dwarf irregular galaxies we observe today are at various stages in this evolutionary journey, and by studying them, we can piece together the life cycle of small galaxies throughout the universe. These tiny systems may seem insignificant, but they represent the fundamental building blocks from which larger galaxies like our own were assembled. As we move away from the realm of dwarf irregular galaxies, we carry with us an appreciation for these small, chaotic systems. They may lack the grandeur of spiral galaxies or the ancient dignity of ellipticals, but dwarf irregulars are vital components of the cosmic ecosystem. They are the galaxies where star formation continues in conditions similar to those of the early universe. They are the building blocks that merge together to create larger galaxies. They are the laboratories where we test our understanding of dark matter, chemical evolution, and the fundamental physics of star formation. Dwarf irregular galaxies remind us that the universe operates on many scales simultaneously, and that some of the most important insights come from studying the smallest and most humble objects. Now, let us contemplate the forces that bind our local group together, and the dance of gravity that governs the motions of all these galaxies. We have now visited many of the individual members of the local group, from the giant spirals to the tiniest dwarf galaxies. But the local group is more than just a collection of isolated objects. It is a gravitationally bound system, a cosmic family held together by the invisible force of gravity. Every galaxy in the local group is in motion relative to every other galaxy, their paths determined by the combined gravitational pull of all the mass in the system. This is a complex, many-body problem, one that cannot be solved with simple equations. Instead, astronomers use computer simulations to model the motions and interactions of the galaxies, tracing their orbits backward into the past and forward into the future. What emerges from these simulations is a picture of an intricate gravitational dance that has been ongoing for billions of years. At the heart of the local group's dynamics are the two dominant galaxies, the Milky Way and Andromeda. These two giants contain most of the mass of the local group, and their mutual gravitational attraction dominates the motion of the entire system. The local group as a whole is moving through space, but internally, the galaxies orbit around a common center of mass located somewhere between the Milky Way and Andromeda. The smaller galaxies in the group are influenced primarily by the gravity of these two giants, orbiting around them like planets around a binary star system. The triangular relationship between the Milky Way, Andromeda, and Triangulum adds additional complexity, and the precise orbital configurations are still not fully understood. What is clear is that the local group is a dynamic system, constantly evolving as its constituent galaxies move and interact. The satellite galaxies orbiting the Milky Way and Andromeda follow elongated, elliptical paths that take them far out into the intergalactic void before bringing them back in close to their host galaxies. During these close passages, tidal forces from the larger galaxy can strip away stars and gas from the satellite, gradually dismantling it over many orbits. This process of tidal stripping has created the stellar streams we see in the halos of large galaxies, faint ribbons of stars tracing out the orbital paths of destroyed dwarf galaxies. The Magellanic stream, which we discussed earlier, is one example of this process in action. As the large and small Magellanic Clouds orbit the Milky Way, they leave behind a trail of gas that eventually will fall back onto the Milky Way's disk. This is how large galaxies grow, by consuming their smaller neighbors and incorporating their material. Not all galaxies in the local group are satellites of the Milky Way or Andromeda. Some of the dwarf galaxies appear to be following independent orbits through the local group, not permanently bound to either of the two giants. These galaxies may have closer approaches to one of the large galaxies in the future, or they may remain independent for billions of years. The orbital dynamics of the local group are sufficiently complex that precise predictions are difficult, especially for the smaller galaxies where measurement uncertainties in distance and velocity are significant. What we observe is a snapshot of the local group at one particular moment in time, and from this snapshot, we must try to reconstruct the past and predict the future. It is a challenging task, but one that yields profound insights into the evolution of galaxy groups. The role of dark matter in the local group's dynamics cannot be overstated. The visible stars and gas we see in galaxies represent only about 1/6 of the total mass of the local group. The remainder is dark matter, distributed in massive halos around each galaxy and filling the space between them. It is the gravity of this dark matter that ultimately controls the motion of the galaxies. Without dark matter, the observed velocities of galaxies in the local group would not make sense. The galaxies would be moving too fast to remain bound to each other, and the group would have dispersed billions of years ago. Dark matter provides the gravitational glue that holds the local group together, even though we cannot see it directly. Its presence is inferred from its gravitational effects, and these effects are everywhere in the dynamics of our galactic neighborhood. Over time, the gravitational interactions between galaxies in the local group lead to dynamical friction, a process where moving galaxies gradually lose energy through their interactions with the surrounding matter. This causes the orbits of satellite galaxies to gradually decay, bringing them closer and closer to their host galaxies over billions of years. Eventually, many of these satellites will merge with their hosts, adding their stars to the larger galaxy. This is not a sudden, catastrophic event, but a slow, gradual process that unfolds over cosmic timescales. The Milky Way has experienced many such mergers in the past, and it will experience many more in the future. Each merger leaves its mark on the structure and properties of the surviving galaxy, contributing to the complex, layered structure we observe in large galaxies today. The local group itself is not isolated. It is part of a larger structure known as the Virgo supercluster, a vast collection of galaxy groups and clusters spanning over 100 million light-years. The Virgo supercluster is dominated by the Virgo cluster, a massive concentration of galaxies lying about 50 million light-years from the local group. The gravity of the Virgo cluster influences the motion of the local group as a whole, pulling it slowly in the direction of Virgo. However, recent observations have revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters that includes over 100,000 galaxies. The local group is a tiny component of this vast cosmic structure, and our motion through space is influenced by the gravitational pull of matter on scales far beyond our immediate neighborhood. We are connected to the universe on every scale. The dance of gravity that governs the local group is beautiful in its complexity. Each galaxy moves according to the combined influence of every other mass in the system, creating patterns that are both orderly and chaotic. Orbits precess, encounters occur, and the structure of the group slowly evolves. This is not a static picture, but a living, breathing system in constant motion. And the most dramatic act of this cosmic ballet is yet to come. In the future, the Milky Way and Andromeda will collide, fundamentally reshaping the local group and creating a new, merged galaxy from the union of these two giants. Let us now turn our attention to this future collision and contemplate what it means for our cosmic neighborhood. 4 billion years from now, give or take a few 100 million years, the Milky Way and Andromeda will collide. This is not speculation. It is a prediction based on careful measurements of Andromeda's motion through space. The two galaxies are approaching each other at about 110 kilometers per second, and at this rate, they will eventually close the 2.5 million light-year gap between them. When they meet, it will be one of the most spectacular events in the history of the local group, a collision between two massive spiral galaxies that will reshape the structure of our cosmic neighborhood. But what will this collision look like? Will it be violent and destructive? The answer might surprise you. Galactic collisions, while dramatic on a cosmic scale, are relatively gentle events on the scale of individual stars. When we say that galaxies collide, we do not mean that stars collide. Galaxies are mostly empty space. The distance between stars is so vast compared to the size of the stars themselves that the probability of any two stars actually hitting each other during a galactic collision is vanishingly small. Instead, what collides is the overall gravitational potential of the two galaxies. As the Milky Way and Andromeda interpenetrate, their gravitational fields will interact, creating tidal forces that distort and reshape both galaxies. Stars will be flung out into enormous tidal tails, gas clouds will be compressed and triggered into furious bursts of star formation, and the structures of both galaxies will be dramatically altered. But individual stars, including our Sun, will simply find new orbits in the merged system. The collision will be spectacular to observe, but locally, for any planets orbiting any particular star, it will be a relatively calm event. Computer simulations of the Milky Way Andromeda collision have been run many times, and they all show a similar sequence of events. The two galaxies will make an initial close pass, swinging around each other under their mutual gravity. During this first encounter, both galaxies will be tidally distorted, with long streams of stars pulled out from the main bodies. The galaxies will then separate again, moving apart for hundreds of millions of years before their gravity pulls them back together for a second collision. This process may repeat several times, with each pass bringing the galaxies closer together and causing more disruption. Eventually, after perhaps 1 billion years of these encounters, the two galaxies will merge completely, their stars and gas thoroughly mixed. What will emerge from this merger is a single, giant, elliptical galaxy, no longer possessing the elegant spiral structure of its progenitors. The collision will trigger massive bursts of star formation as gas clouds from both galaxies collide and compress. These starbursts will create millions of new stars over a relatively short period of cosmic time, dramatically increasing the rate of star formation above the normal level. The newly formed stars will be hot, massive, and blue, and they will light up the merging galaxies with brilliant blue light. However, many of these massive stars will have short lifetimes, and they will quickly evolve and explode as supernovae, enriching the interstellar medium with heavy elements. The merger will also affect the supermassive black holes at the centers of both galaxies. As the galaxies merge, the two black holes will eventually sink to the center of the new galaxy and spiral together, ultimately merging into a single, even more massive black hole. This black hole merger will release tremendous amounts of energy in the form of gravitational waves. What will happen to Earth during this collision? The answer depends on many factors, most of which are beyond prediction over such long timescales. However, we can make some educated guesses. The Sun will be about halfway through its main sequence lifetime when the collision occurs, and it will have grown somewhat hotter and more luminous. Earth's climate will have been affected by this increased solar output, and it is possible that the oceans will have evaporated, making the planet uninhabitable for life as we know it. This fate is independent of the galactic collision. As for the collision itself, Earth's orbit around the Sun is unlikely to be significantly affected. The Sun may find itself in a different part of the merged galaxy, perhaps farther from the galactic center or in one of the extended tidal tails, but the solar system itself should remain intact. Any civilizations that exist at that time will have a spectacular view of the cosmic fireworks, the merged galaxy that results from the Milky Way. Andromeda collision has already been given a name by astronomers, a nickname coined long before the merger will occur. It is called Milkomeda, a portmanteau of Milky Way and Andromeda. Milkomeda will be a giant elliptical galaxy, one of the largest galaxies in the local group's region of the universe. It will contain over 2 trillion stars, more than twice the current combined, stellar population of its progenitors. The reason for this is that the starburst triggered by the merger will produce vast numbers of new stars from the available gas. Eventually, however, most of the gas will be consumed or ejected, and star formation in Milkomeda will gradually cease. The galaxy will become red and dead, composed primarily of old, low-mass stars slowly fading over trillions of years. What will happen to Triangulum during the Milky Way? Andromeda merger? This is one of the uncertainties in the predictions. Triangulum may be swept up in the collision, becoming part of the final merged galaxy. Alternatively, gravitational interactions during the merger may fling Triangulum outward, ejecting it from the local group to wander the intergalactic void as an isolated galaxy. Computer simulations suggest both outcomes are possible, depending on the precise timing and geometry of the interactions. The fate of the third spiral is uncertain, but one thing is clear. The local group as we know it will be fundamentally transformed. The merger of the Milky Way and Andromeda will mark the end of one era and the beginning of another, a transition from a group of distinct galaxies to a single dominant structure surrounded by smaller satellites. The collision between the Milky Way and Andromeda is part of a larger pattern playing out across the universe. Galaxy mergers are common events in cosmic history, and they are one of the primary mechanisms by which galaxies grow and evolve. In the early universe, small proto-galaxies merged together to form larger systems. Over billions of years, these larger systems continued to merge, building the massive galaxies we see today. The process continues into the present and will continue into the future. The Milky Way. Andromeda collision is simply the next chapter in this ongoing story of galactic evolution. It is a reminder that galaxies are not eternal, unchanging structures. They are dynamic, evolving systems that transform over cosmic time. What we see today is just one moment in a much longer story, and the future holds dramatic changes that will reshape the cosmic landscape in ways we can only begin to imagine. As we drift through the local group, having visited its galaxies and contemplated its future, we find ourselves enveloped in a profound sense of tranquility. Despite all the drama we have discussed, the collisions and mergers, the birth and death of stars, the actual pace of change in the universe is extraordinarily slow by human standards. The collision between the Milky Way and Andromeda will unfold over billions of years. A human lifetime is barely a blink in cosmic time. From our perspective, the universe appears almost perfectly still, a frozen tableau of galaxies hanging in the darkness. This is the great paradox of astronomy. We study change and evolution on scales so vast that in our brief moment of consciousness, everything appears eternal and unchanging. There is something deeply calming about this realization. The local group is our cosmic home, but it is also a place of profound isolation. The nearest galaxy group to ours is the M81 group, lying about 12 million light-years away. That is almost 5 times the diameter of the local group itself. Beyond that lie other groups and clusters, scattered across hundreds of millions of light-years. The space between galaxy groups is almost perfectly empty, containing perhaps a few wandering galaxies, but mostly just the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang. If you could stand in the intergalactic void between groups, you would see perhaps 1 or 2 faint smudges of light in the entire sky. The rest would be darkness. The universe is unimaginably vast, and most of it is empty space. We live on an island in an immense ocean. There is something meditative about contemplating the scale of the local group. We have traveled from galaxy to galaxy, visiting worlds of stars separated by millions of light years, and yet the entire local group is just a tiny speck in the observable universe. The observable universe extends for over 90 billion light years in diameter and contains an estimated 2 trillion galaxies. The local group is one small family among countless others, and beyond the observable universe, there may be infinitely more space, infinitely more galaxies, forever beyond our ability to see or know. When faced with such immensity, the problems and concerns of daily life seem to shrink away, becoming insignificant against the backdrop of cosmic vastness. This is not nihilism, this perspective. It is the realization that we are part of something much larger than ourselves. The local group has existed for over 10 billion years, and it will continue to exist in some form for trillions of years into the future. Long after the sun has died, long after Earth is gone, the galaxies of the local group will still be here, slowly evolving and merging. Stars will continue to form from collapsing gas clouds, live their lives, and die, returning their material to the interstellar medium. Black holes will continue to lurk in galactic centers, occasionally flaring to life when they consume nearby matter. Supernovae will explode, briefly outshining entire galaxies. The cosmic dance will continue, indifferent to the presence or absence of observers. The universe does not need us to exist. It existed for billions of years before we arrived, and it will continue for trillions of years after we are gone. And yet, here we are, conscious beings capable of understanding and appreciating this vast cosmic structure. One of the most profound realizations we can have when contemplating the local group is that we are not separate from it. We are not outside observers looking at something distant and alien. We are inside it. We are made of it. Every atom in your body was forged in the core of a star somewhere in the Milky Way or in one of the dwarf galaxies that merged with it in the distant past. The calcium in your bones was created in a supernova explosion billions of years ago. The iron in your blood was synthesized in the dying moments of a massive star. The oxygen you breathe was produced by countless generations of stars over cosmic history. You are not in the universe. You are the universe, a localized concentration of matter that has become self-aware and capable of contemplating its own origins. This is the deepest connection imaginable. The silence of space is absolute. There is no air to carry sound waves, no medium through which vibrations can travel. If you could float here in the intergalactic void, you would hear nothing. Not the faintest whisper. This silence is not oppressive or frightening, peaceful. It is peaceful. It is the silence of a universe that simply exists without need for explanation or justification. In our daily lives, we are constantly bombarded by noise, by information, by demands on our attention. But here, in the space between galaxies, there is only silence and stillness. It is a silence that invites contemplation, that creates space for deep thought and reflection. In the silence of the cosmos, we can hear our own thoughts more clearly. We can connect with something fundamental and timeless. The beauty of the local group lies not just in its grand structures, the spiral galaxies and star-forming nebulae, but also in the empty spaces between them. The darkness between galaxies is not truly dark. It contains the faint glow of the cosmic microwave background, the oldest light in the universe, dating from just a few 100,000 years after the Big Bang. This faint radiation fills all of space, carrying information about the conditions in the early universe. When we observe the darkness between galaxies, we are seeing the afterglow of creation itself, cooled and stretched by billions of years of cosmic expansion. Even the empty spaces in the universe are not truly empty. They are filled with history, with memory, with the echo of the moment when space and time began. Everything is connected to everything else across all scales of space and time. As we prepare to conclude our journey through the local group, take a moment to simply exist here in the cosmic stillness. There is nowhere you need to be, nothing you need to do. Just float here in the space between worlds, surrounded by the soft light of distant galaxies, and allow yourself to feel the peace that comes from contemplating something infinitely larger than yourself. The local group will continue its slow evolution whether we observe it or not. The galaxies will continue their gravitational dance, stars will be born and die, and the universe will expand ever onward into an unimaginable future. But for this moment, we are here, conscious witnesses to the beauty and wonder of creation. Let yourself be still. Let yourself be calm. Let yourself be part of the cosmic whole, We have journeyed together through the local group, visiting galaxies both grand and humble, contemplating the forces that bind them together and the future that awaits them. Now, as our tour comes to an end, it is time to reflect on what all of this means. What is our place in this cosmic structure? Why does it matter that we understand the local group? These are not just scientific questions. They are philosophical questions, questions about meaning and purpose in a universe that is vast beyond comprehension. The local group is our context, the larger structure within which our existence unfolds. To understand the local group is to understand where we fit in the grand scheme of things, and perhaps to find some measure of peace in that understanding. One of the most important things we learn from studying the local group is humility. We live on a planet orbiting an ordinary star in an ordinary spiral galaxy. Our galaxy is part of a small group containing just a few dozen significant members, and this group is just one among countless others scattered throughout the universe. On cosmic scales, we are utterly insignificant, a brief flicker of consciousness in a universe that existed for billions of years before us and will continue for trillions of years after us. This could be seen as depressing, but it does not have to be. There is a certain freedom in insignificance. If the universe does not care whether we exist, then we are free to define our own purpose and meaning. We are free to create, to love, to explore, to wonder. Our insignificance is not a burden. It is a liberation. But while we may be small, we are also extraordinary. As far as we know, we are the only conscious observers in the local group, perhaps even in the entire observable universe. We are the means by which the universe has become aware of itself. Through our telescopes and our mathematics, through our curiosity and our capacity for wonder, the universe is able to look back at its own structure and marvel at its own beauty. Every time you gaze up at the night sky and feel a sense of awe, you are participating in this cosmic self-awareness. You are the universe contemplating itself. This is not a metaphor. This is literally true. The atoms that make you were forged in stars, and now those atoms have organized themselves into a structure capable of understanding where they came from. That is astonishing. That is miraculous. The local group reminds us that we are not alone, even if we have not yet found other intelligent life. We are part of a family of galaxies, a cosmic community bound together by gravity and shared history. The Milky Way has companions, neighbors, satellites. We orbit together around a common center of mass, our fates intertwined. This is true on every scale. Earth is part of the solar system. Earth. The solar system is part of the Milky Way. The Milky Way is part of the local group. The local group is part of larger structures stretching across the observable universe. We are nested within nested structures, each level of organization providing context for the next. We exist within a cosmic web of connections, and understanding these connections helps us understand our place in the whole. The study of the local group also gives us perspective on time. Humans live for decades. Civilizations last for centuries or millennia. But galaxies exist for billions of years. The processes we observe in the local group unfold over timescales that are almost incomprehensible to beings with our limited lifespans. The collision between the Milky Way and Andromeda will take place 4 billion years from now, a span of time equal to the entire history of the Earth. When we contemplate such vast stretches of time, our daily concerns and worries seem to fade in importance. The problems that consume our attention today will be forgotten in a century. The civilizations we build will crumble in millennia, but the galaxies will endure. There is something deeply humbling and strangely comforting about this perspective. What can we take from our tour of the local group and apply to our daily lives? Perhaps it is simply this: take time to look up. Step outside on a clear night and gaze at the stars. Try to identify the faint smudge of Andromeda in the constellation of the same name. Look for the Magellanic Clouds if you're in the southern hemisphere. Remember that the light entering your eyes left those galaxies millions of years ago when Earth was a very different place. Remember that you are seeing not just distant objects, but distant times, looking into the past with every photon that reaches you. Feel the connection across space and time. Let yourself be awed by the scale and beauty of it all. In those moments of cosmic contemplation, you might find a sense of peace and perspective that is increasingly rare in our busy, distracted world. The local group is a reminder that the universe operates on principles that are both simple and profound. Gravity pulls matter together. Stars form, shine, and die. Galaxies merge and evolve. These processes follow physical laws that we have been able to discover and understand through careful observation and mathematical reasoning. The fact that the universe is comprehensible, that we can understand it through science, is itself remarkable. The universe could have been chaotic and random, but instead it follows patterns and rules that our minds are capable of grasping. This suggests a deep harmony between the structure of the cosmos and the structure of consciousness. We are not aliens in a hostile universe. We are natural products of cosmic evolution, and our ability to understand the universe is part of that evolution. In understanding the local group, we are fulfilling our cosmic purpose. As we bring our journey through the local group to a close, remember that this is not an ending, but a beginning. Every time you look up at the night sky, you can return to these places in your imagination. You can float among the galaxies, contemplating their beauty and their stories. You can think about the slow dance of gravity that binds them together, the ancient light that travels between them, and the future that awaits them billions of years from now. The local group is always there, always accessible to those who take the time to look and wonder. It is a source of perspective, of humility, of awe, and of peace. May your journey through the cosmos continue, and may you always find calm in the contemplation of the stars. The universe is vast. You belong here, among the galaxies, a child of the stars looking back at the cosmic family from which you came. Thank you for joining me on this serene journey through the local group, our cosmic neighborhood. If this exploration brought you peace, wonder, or a moment of escape from the everyday, consider subscribing to Cosmic Calm for more long-form space documentaries designed for sleep, relaxation, and quiet contemplation. Share this video with someone who might need a moment of cosmic tranquility. And remember, whenever you need to find perspective or peace, the universe is waiting for you. The galaxies are always there, drifting through the darkness, and you are always welcome to return. Until our next journey together, may you find calm in the cosmos.